think about f of x equals the natural log of x. Now we run into trouble here. I can't write this as a Maclaurin series because I can't take f of 0. It doesn't exist. So let's center this guy. Let's center at, I don't know, x equals 1. So basically what we're saying is, parenthetically, is a equals 1. All right? So first things first. We always do it the same way. By the time I'm done, let's write a 5th degree Taylor polynomial for this. So the way that that's written, it's written kind of strange. It's t sub 5 of x, which is going to be approximately equal to f of x, which equals the natural log of x. So this is the notation. This just basically says 5th degree Taylor polynomial. That gets a little tricky to play with, and I'll show you why down the road. But just for now, know that this is kind of like, remember when we did 5 left rectangular approximations, we used L5. There's just a subscript there to tell us how many we need. So that means we're going to have to take how many derivatives? We're going to theoretically have 6 terms, and we're going to take 5 derivatives. But that's not bad. Let's kind of do it all at once, shall we? So f of x equals ln x, right? F primed of x is equal to 1 over x. F double primed of x is equal to negative 1 over x squared. The third derivative of x is equal to what? Positive 2 divided by x cubed. Do you agree with that? I'll buy that. F, the fourth derivative of x, is equal to negative 6 divided by x to the 4th, right? You see how I'm doing this? Just traipsing on through. And then the 5th derivative of x is equal to a positive 24 over x to the 5th. Now, let's do f prime. Well, let's do f of 1. That's easy. That's 0. F primed of 1 is 1. F double primed of 1 is negative 1. The third derivative at 1 is positive 2. The fourth derivative at 1 is negative 6. Ooh, I'm liking this. Look at how that changes signs. The fifth derivative at 1 is positive 24. Wow, well that's interesting. So I've got this. That tells me that the natural log of x can be written as 0 plus 1 over 1 factorial times x minus 1. Minus 1, let's not get too crazy. You ready? This is where we get crazy. Minus 1 times x minus 1 squared over 2 factorial plus 2 times x minus 1 cubed over 3 factorial. See what I'm doing here? Excuse me. Minus 6 times x minus 1 to the 4th over 4 factorial. Ooh, I'm starting to see an interesting pattern here. Plus 24 times x minus 1 to the 5th over 5 factorial. Now, I could pretty these up if I wanted to, right? I could write this as, oh, good golly gracious sakes. Well, let's play first. I could write this as x minus 1 minus 1/2 x minus 1 squared plus 2/3 x minus 1 cubed minus, now there's going to be some cancellation in here, right? This is going to be minus 1/4 x minus 1 to the 4th, and then I don't even want to mess with that. What's that? Over 1/5? You buy, oh, yeah, over plus 1/5, right? Oh, wow. That's crazy. So that's pretty cool, right? I mean, I just wrote the natural logs as, I wrote it as equal. It's really approximately equal to. Because if I wanted to make it equal to it, I would have to do the natural log of x equals, and then what I would have is, I would have that remainder term. Remember how we talked about Rn of x before? This is the error. This is how much I'm off by when I stop at a fixed n. Now, look real close, because something fascinating happens here. Notice my denominator is 1 factorial, 0 factorial, 1 factorial, 2 factorial, 3 factorial. That's 3 factorial. That should have been 1/3, shouldn't it have? 4 factorial, 5 factorial. But what else do you know? Well, let's ignore the 0 because it disappears. Do you notice that it changes signs? So if I wanted to write the general term as n goes from 0 to infinity. Now let's think about this. The first term is positive. The second term is negative. Third term is positive. Fourth term is negative. So I'm going to write this as negative 1 to the n plus 1. That accounts for the changing of the signs, right? I'm definitely going to have an x minus 1. Since I started it at 0, I have now officially committed. I could start it at 1 if I wanted to, right? I could start it at 1. Now that would change the behavior of this. But I'm going to stick with my commitment, okay? So let's make sure. Oh, wait, I started at 0, get 1. Wait, if I do that, you know what? If I started at 0, I got to catch myself. Then this guy's got to be just n, right? Because I started it at 0. Ooh, nice catch, Ripley. You're good. If I start at 0, I get x minus 1 to the first. Cool. When it's 2, or when n is 1, I get x minus 1 squared. When n is 2, I get x minus 1 cubed, etc., etc. Now, there's something funky that happens here. What do you notice here? I'm going to give you a hint. Look close. I see a pattern here. As soon as I saw this 1, 1, 2, 6, 24, my spidey sense started tingling, and I started saying, is that really 0 factorial? Is this really 1 factorial? Is this really 2 factorial? And this is 3 factorial, and this is 4 factorial. So what appears to be happening here, I'm going to erase myself a little spot here so I get a little more space, sorry. What appears to be happening is, what did I say? This is x minus 1 to the n plus 1, right? Is what's going on. When n is 0, I get 0 factorial, right? Over 1 factorial. When n is 2, when n is 1, I get 1 factorial over 2 factorial. When n is 2, I get 2 factorial over 3 factorial. When n is 3, 3. Whoa, that's crazy. So it appears that I'm getting n factorial over n plus 1 factorial. But isn't n plus 1 factorial just n plus 1 times n factorial? So this whole thing for my general term can be written as n equals 0 to infinity, negative 1 to the n, isn't that crazy? X minus 1 to the n plus 1, and since I've got n factorial over n plus 1 times n factorial, the n factorials cancel, and I just get the whole thing over n plus 1. Now remember, don't take my word for it. I could be lying. And this stuff's, I am not so glib as to say, oh yeah, they're going to get this immediately. You're going to play with this. You're going to struggle with it. You're going to have difficulties. It's okay. If you don't believe me, let's list the terms and see if we get this guy back out. Okay, so here we go. Let's see, when n equals 0, that's going to be a 1. I'm going to get 1 times x minus 1 to the first divided by 1. Oh, sweet, perfect. So, check. First term, taken care of. Plus, whoa, I don't know what just happened there. What is that? Plus, here we go. Plus, when n is 1, I get negative 1. Ooh, so it's not even a plus, is it? It's a minus. Wow, my pen is freaking out today. It's going to be a minus. So I get minus. Now, let's see, I get x minus 1 to the, let's see, when n is 1, that's going to be squared, divided by 2. Hey, that works out really well. What's my next term going to be? When n equals 2. Well, now I've got negative 1 squared, so it's going to be plus 1 times, oh, wait, but I need to account for this 2 factorial here. No, I don't. No, I don't. Don't even listen to Ripley. I'm crazy. Let's see, 1 times x minus 1 to, what did I say, when n is 2. So I'm going to get x minus 1 cubed divided by 3. Now let's make sure that that's true. 2 factorial, which is 2 divided by 3 factorial. Yeah, that's just the third. Yeah. Minus 1 times x minus 1 to the fourth. That's awesome. Now, one last little cool thing, and then I'm done. I know I'm driving you guys crazy. Watch this. The coolest thing here is, let's say that I want to approximate. Watch this. I'll finish up. We know that the natural log of x, the general term for this guy, is the sum as n goes from 0 to infinity, negative 1 to the n, x minus 1. This is centered at 1, right? X minus 1 to the, what do we say, n plus 1 divided by n plus 1, right? Well, I know that the radius of convergence on this guy is 1, which you could prove really easily. I mean, check it out. All the rules for trying to figure out what radii of convergence are, what intervals of convergence, all that good stuff are still in effect. So if I wanted to do the ratio test on this guy, I could. You can probably see, I don't know how extensive your experience is yet, but what you're going to end up with is x minus 1 is going to, absolute x minus 1 is going to be less than 1. Now, we're not going to get into that because I don't want to, you guys will go nuts if I do that. However, think about that. That means if I've got the natural log of x, right, so this is f of x equals ln of x, and I want to approximate the natural log of 1/2, right, using a polynomial. This is powerful good stuff. Well, look, all I got to do is, wherever I see an x in my polynomial, stick it in there. This becomes a sum as n goes from 0 to infinity of -1 to the n times, 1/2 minus 1 to the n plus 1 divided by n plus 1. I have a new series. This guy turns into the sum as n goes from 0 to infinity of -1 to the n times -1/2 to the n plus 1, all divided by n plus 1. And then you can sort of see what's going to happen here. I mean, if I wanted to, I could pull out -1s and combine this up. But this turns into something where we could just list terms. You know, when n equals 0, what's this thing equal? It equals -1/2. When n equals 1, this is -1 times a positive 1/2. That's a -1/2 over 2. What's that? What do we got? A positive 4? Is that right? No, negative 1/4. Is that right? I mean, think about kind of the uses of all of this. It's incredible. All right, so just wanted to give you an idea how these Taylor polynomials work. We're going to do a bunch of stuff in class. It'll be a hoot. It'll be a holler, I promise. Thanks for your time and attention, and have a really good day, and we'll see you in class tomorrow. Bye-bye.